so the topic of my talk is well-dominated graphs. And I'm a professor in the computer engineering department of Gebze Technical University. And thank you very much for inviting me for this talk. I will start with definitions and an introduction about domination in general, a little bit, but mostly on well-dominated graphs. And then I will talk about some literature on characterization of well-dominated graph classes. Then I will mostly discuss more in detail about one of my works, which is well-dominated lexicographic products. And then also briefly about two of my the other works, which are related to well-dominated graphs, which is a generalization. They are called almost well-dominated graphs. So G is, as usual, a simple graph with vertex set VG and edge set EG. The open neighborhood of a vertex is the set of vertices that are adjacent to B. So we don't have the vertex itself in the open neighborhood, but in the closed neighborhood, we have the open neighborhood, its neighbors, union the vertex itself as well. So the degree of a vertex is the total number of its neighbors, and minimum degree is denoted by delta G. The girth of a graph is the length of its shortest cycle. So a dominating set, a subset of vertices, is called a dominating set if every vertex that are not in the set has at least one neighbor in the set. And gamma G is called the domination number and is the size of a minimum dominating set. For example, in the graph on the left, we see a dominating set with size 2. And in the middle, for the same graph, we see another dominating set, which is also of size 2. But if we look at the graph on the right, we see that it's not a dominating set because the vertex in the diagonal of that cycle is not dominated. So what is a minimal dominating set? A dominating set is called a minimal dominating set if it does not contain any smaller dominating sets. So it's a set theoretical property. For instance, we can see in this example that this is a dominating set, and is it a minimal dominating set? Yes, because if we remove any one of these three vertices, then the remaining is no longer a dominating set. So in here also we see another dominating set, which is also a minimal dominating set. So we can see that we can have minimal dominating sets with different sizes. A minimal dominating set with maximum size is called maximum minimal dominating set, or in other words, upper domination number of G. And it's denoted as big gamma of G. For example, for the same graph, we can see that the upper domination number is 3. And because first of all, this is a minimal dominating set and it's of size 3. And secondly, it's not possible to find a larger minimal dominating set, a minimal dominating set with a larger size. But for the same graph, we see that a minimum dominating set, its domination, which is the domination number, is 2. So for this graph, the domination number is 2 and its upper domination number is 3. So in general, these two may differ. So an independent set in a graph is a subset of vertices. They are called independent sets if no two vertices in the set are adjacent to each other. And independence number is size of a maximum independent set. For example, on the graph on the left, we see that this is not an independent set because these two black vertices are adjacent to each other. So it's not an independent set. Whereas for the graph in the middle, we see that these two vertices are not adjacent to each other, so they're not an independent set. And also for the graph on the right, we have just one vertex, which by definition is an independent set. because there's no other vertex that it can be adjacent to. That is also a black vertex. So a maximal independent set is an independent set that is not a subset of any other independent set. So it also means that it's an independent set, but if we try to add one more vertex to this set, it's not possible that we get an independent set. So for this graph on the left, for instance, whichever of these vertices we want to add to this remaining set, it's going to be adjacent to at least one of these vertices. So it's a maximal independent set. Whereas for the graph on the right, we see that if we try to add one vertex that is not on the diagonal of this vertex that is in the independent set, we are able to add it. So we are able to add one more vertex to this set. So it's not a maximal independent set, the one on the right. So a maximum independent set is an independent set with maximum size, and it's denoted by alpha G. Whereas a minimum maximal independent set is a maximal independent set with minimum size, and it's denoted by little ig. For instance, for this graph, we see that it is possible to find an independent set with size 3, and we can't find an independent set with size at least 4. So this is a maximum independent set. But we can also see that this is another maximal independent set, and it's of size 2. So, and it's actually a minimum maximal independent set. So these two also may be different from each other. So the domination chain, widely used concept in domination. For any graph, the following holds. The domination number is less than or equal to the size of the minimum maximal independent set, which is also called the independent domination number, by the way, the little ig, is less than or equal to the independence number, and that is less than or equal to the upper domination number. So what is a well-dominated graph? A graph is called well-dominated if all its minimal dominating sets are of the same size. That is, if the little gamma is equal to the big gamma of G, then the graph is called well-dominated. And another definition, a graph is called well-covered if all its maximal independent sets are of the same size. That is, if little ig is equal to alpha of G. So actually, because since every maximal independent set is a minimal dominating set, it can be proved very easily. Well-dominated graphs form a proper subclass of well-covered graphs. Actually, we can also see this from the domination chain. So if the little gamma and big gamma are equal to each other, then definitely little I and alpha also have to be each other. So it means that if the graph is a well-dominated graph, then definitely it's also a well-covered graph. But if it's a well-covered graph, if its ig and alpha g are equal to each other, then it does not necessarily mean that little gamma and big gamma also need to be each other. So not every well-covered graph is a well-dominated graph, but every well-dominated graph is a well-covered graph. So well-dominated graphs were introduced by Fimbo in 1988, and in which they characterized well-dominated graphs of girth at least 5 and characterized well-dominated bipartite graphs and showed that within graphs of girth at least 6, well-dominated graphs coincide with well-covered graphs. So if we say that let G be a graph that is of girth at least 6, then G is well-dominated if and only if it is well-covered. So for that particular condition, they are the same. And well-dominated block graphs, let Cg be the cut vertices of G, and we can say that if we take the open neighborhood of V in G and remove the cut vertices, we call them NCG. Jerzy-Top and Folkman in 1990 proved that for a block graph, the following statements are equivalent. little gamma is equal to big gamma, meaning that it's well dominated. And little gamma is equal to alpha G. Ig is equal to alpha G, meaning that it's well covered. So for block graphs also, they are equivalent. It means well dominated and well covered. And little Ig is equal to big gamma G. So these statements are all equivalent. And the vertex sets of the exterior blocks of G form a disjoint partition of the vertex set. And the induced subgraph NCGV of the graph is non-empty and complete for every cut vertex of G. So well-dominated block graphs were also completely characterized. So in that same work, they also characterized well-dominated unicyclic graphs. So they said that the following are equivalent. Ig is gamma G and Ig is alpha G, or G is cycles with sizes 3, 4, 5, and 7. By the way, C3, C4, C5, and C7 are the only well-dominated cycles. And they are also the only well-covered cycles. So these are just the cycles. But apart from that, if we also have other vertices than the cycle in the unicyclic graph, then they also, I'm not going to give the definitions of this, but they provided graph families for that. So they provided a complete structural characterization by providing families of graphs for well-dominated unicyclic graphs. So in another work, about well-dominated four-connected graphs, they characterized four-connected, four-regular, claw-free, and well-dominated graphs. And Finbo and Van Bommel characterized well-dominated planar triangulations. And Levitt and Tankus characterized well-dominated graphs without cycles of lengths 4 and 5. So now I will start talking about well-dominated lexicographic product graphs. So given a graph, so some definitions as well, a few. Given a graph without isolated vertices, a set is called a total dominating set if every vertex of G has a neighbor in D. So for instance, in the first graph here, it's not a total dominating set because the ones in the dominating set, their neighbors are white, all white. So for a total dominating set, if we look at the subgraph induced by the vertices in the total dominating set, then we don't have any isolated vertices, but this is not the case for the first graph. Whereas for the second graph, we can say that, that this is a total dominating set, because every vertex in the dominating set also has at least one neighbor that is also in the dominating set, which makes it a total dominating set. So the total domination number of G is the size of the minimum total dominating set, which may also be different. A total dominating set is a minimal total dominating set if similarly for minimal dominating sets, this time it's that if no proper subset of it is a total dominating set. So some proper subset might be a dominating set, but if it's not a total dominating set, then it's called a minimal total dominating set. So the property of being a total dominating set cannot be preserved if we remove one vertex. Well-dominated lexicographic product graphs. For a vertex V, we say that vertex V is totally dominated by D, or that big D totally dominates V, if V is adjacent to at least one vertex in the dominating set. So the set D totally dominates V. Moreover, we say that V is barely dominated by D, by definition, if V is dominated but not totally dominated by D. That is, if V is an isolated vertex in the subgraph of G induced by D, then we say that it's barely dominated. So let me give the definition of a lexicographic product. the lexicographic product of two graphs G and H is the graph with vertex set VG Cartesian product VH, where two vertices x1, y1 and x2, y2 are adjacent if and only if either there is an edge between x1 and x2, or x1 is equal to x2, and there is an edge between y1 and y2 in H. So in this example, for instance, we see that P2, P3. So like this, if P2 is G and P3 is H, then the one in the middle, it's the lexicographic product. And we also see P3, P2. So as it is evident from this example, the lexicographic product of two graphs may not be commutative. So let's talk about some work in product graphs in domination, and mostly on Cartesian product and Wissing's conjectures. There are some works from 2012 from Bossam and Bressar. And for lexicographic product graphs, various types of domination were investigated, such as the following: domination in 1996 and 2012, rainbow domination, Roman domination, restraint domination, and in particular, the works Sumenjak et al. And Zhang et al. Imply that the value of the domination number of a non-trivial lexicographic product of two graphs can be exactly determined as a function of the domination and total domination numbers of its factors. So I would like to talk about the recognition problem for well-covered and well-dominated graphs. So one wonders whether recognizing such graphs can be done in polynomial time. Actually, it was proved independently in 1992 and 1993 that the recognition problem for the class of well-covered graphs was shown to be co-NP complete. So the recognition problem for well-dominated graphs was an open question for a long time. And very recently, it was proved to be also to be co-NP complete. By the way, there is another class called well-totally dominated graphs, which means that the size of the minimum total dominating set and maximum minimal total dominating set, which is called the upper total domination number, are the same. So the definition is analogous. And it was proved in that same paper, in that last same paper in 2024, and I think it was in January, that recognizing well totally dominated graphs is also co-NP complete. So summary of some results. So our results in this work on well-dominated lexicographic products. So first of all, we introduced the notion of an irreducible dominating set as a variant of the notion of a dominating set, and it forms a common generalization of both minimal dominating sets and minimal total dominating sets as follows. And we provide a characterization of minimal dominating sets in a non-trivial lexicographic product of two graphs. And building on this characterization, we derive a characterization of the well-dominated non-trivial lexicographic product graphs. And this characterization motivates the study of well-dominated graphs with domination number is equal to 2, for which we develop a polynomially testable characterization. So remember that in general, recognizing well-dominated graphs was proved to be co-NP complete. So for domination number 2, the problem becomes polynomial. And actually, we then generalize this and we show that well-dominated graphs can be recognized in polynomial time in any class of graphs where gamma g is bounded by a constant. So in general, it's co-NP complete, but for this particular case, if gamma g is bounded by a constant, then they can be recognized in polynomial time. So a dominating set is said to be reducible if there exists a vertex such that if we remove that vertex from the dominating set, the remaining is also a dominating set of G, and the set of vertices that are totally dominated by D and D difference U coincide. So we can remove it. It's still a dominating set, and the ones that are totally dominated are also the same. So a dominating set is irreducible if it is not reducible. And we can easily verify that every minimal dominating set is irreducible because if we remove it, the remaining is not a dominating set. And consequently, every dominating set contains an irreducible dominating set because a minimal dominating set is irreducible. And every minimal total dominating set is also irreducible because if you remove that vertex, if it's a minimal total dominating set, if we remove that vertex, the remaining can still be a dominating set, but it's no longer a total dominating set because so this means that the second condition where the set of vertices that are totally dominated right now do not coincide if it's a minimal total dominating set. So therefore, every minimal total dominating set is also irreducible. So that's why it's a generalization of both minimal dominating sets and minimal total dominating sets. Every dominating set whose induced subgraph has maximum degree at most 1 is irreducible. So this can also be verified easily. So the characterization, if you look at the characterization of irreducible dominating sets, which will be useful in characterizing lexicographic product graphs, by the way, that's why we needed this definition of reducible and irreducible. So given a set, a vertex U and a vertex V, we say that V is a D-private closed neighbor of U if the closed neighborhood of V intersection D is equal to the vertex U. Every vertex in D, in the dominating set, with a unique neighbor in D will be called a D-leaf. So we show that for any graph G and a dominating set D, the dominating set is irreducible if and only if every vertex in the dominating set either has a D private closed neighbor or is adjacent to a D leaf. For example, this is an irreducible dominating set. And because if we remove one vertex, it's either not a dominating set or it's not a total dominating set. So, but irreducible dominating set, but it's neither a minimal dominating set nor a minimal total dominating set. So it is one such example. So the projection of a given set, D, in the Cartesian product, it's defined as follows. It's the vertices in X, X in VG, X dimension, such that it's in the dominating set for some Y. For example, we look at the PGD in this example as the dominating set, as the projection of this in G. So for a vertex X in the projection, and this concept of projection is also used very frequently in product graphs. So for a vertex X in the projection, we define that PHXD as the vertices Y such that XY is in the dominating set. So we characterize the dominating sets in the lexicographic product of two graphs as follows. For any two graphs, G and H, a set D in the Cartesian product of the vertices in the product graph, a set D is a dominating set in the product graph if and only if the projection is a dominating set in G, such that for every vertex G that is barely dominated by PGD, the set PHGD is a dominating set in H. So the domination number in lexicographic product graphs, the following theorem can be derived by the previous proposition. If G is a graph without isolated vertices and H is any graph, then the domination number in the lexicographic product is equal to gamma G. If gamma H is equal to 1, it means if there is a universal vertex in H. Otherwise, if it's at least 2, then it's equal to the total domination number. This was proved previously in an earlier work. So let D be an irreducible dominating set in a graph. For a vertex X, we say that X, for a vertex X in the dominating set, in the irreducible dominating set, we say that X is D redundant if D difference X, if you remove X from D, is a dominating set in G. So we prove the following. For any two graphs, G and H, a set D is a minimal dominating set in the lexicographic product if and only if the following conditions hold. First, the projection is an irreducible dominating set in G. Secondly, for every vertex X in the projection, the set PHXD is a subset of size 1 of VH if X is totally dominated by the projection in G, and a minimal dominating set in H if X is barely dominated by the projection. And every PGD redundant vertex is adjacent to a PGD leaf Y, such that the set PHYD is not dominating in H. So this is the characterization of minimal dominating sets in lexicographic product graphs in general. So for about upper domination number in lexicographic product graphs, we see that for every two graphs, G and H, the upper domination number is greater than or equal to alpha G, the independence number of G, times the upper domination number of H. So we can prove it actually, it's not very difficult. So let's look at a maximum independence set in G and call it S. And let's have let A be a minimal dominating set in H of size big gamma H. So a maximum minimal dominating set, actually A. And let D is S product A. So since we can say that the size of S is alpha G, because S is a maximum independent set, and the size of A is big gamma H, because A is a maximum minimal dominating set, is equal to its size is equal to the upper domination number of H. The previous theorem implies that, which characterized minimal dominating set in lexicographic products, it implies that D is a minimal dominating set in GH of size alpha G times big gamma H. So it indeed shows that big gamma in the lexicographic product is at least the max independence number multiplied by upper domination number, independence number of G multiplied by upper domination number of H. So as a remark, we can also say that the value of the upper domination number in the lexicographic product cannot be bounded from above by any function of the product alpha G times big gamma H. For example, we can see that let G be the graph obtained from 2 copies of Kn, 2 copies of complete graphs for n at least 4, joined by a perfect matching, and let H be a cycle of size 4. So then we can see that the upper domination number of the lexicographic product is equal to n, and alpha G times big gamma H is 4. So it cannot be bounded from above by any function of the product. So a non-trivial lexicographic product, we prove that a non-trivial lexicographic product, GH, of a connected graph G, and the graph H is well dominated if and only if one of the following conditions holds. Either G is well dominated and H is a complete graph, or G is a complete graph and H is a well dominated graph with domination number 2. So this brings us to the question about whether we can see or recognize well-dominated graphs with domination number 2, because here H is well dominated with domination number 2. So a graph is well dominated with domination number 2 if and only if the following conditions hold. If the complement of the graph is a triangle-free graph without isolated vertices. So if the complement is a triangle-free graph, it means that the independence number of this graph is 3. So it's without isolated vertices. So independence number is 2, sorry. Or for every 2 triangles, T and T prime in G, such that T union T prime induces the complement of C6. Then this set is not a dominating set in G. So this is one theorem about the structure of such graphs. So the corollary of this is that the problem of recognizing well-dominated graphs can be solved in polynomial time in the class of graphs where the domination number is equal to 2. So remember that in general, it was proved very recently that in general it's co-NP complete. But if the domination number is 2, then we show that it's polynomial. And this brings us the question of, okay, if gamma G is equal to 2, then it's polynomial. But what happens if it's some small domination number, meaning that if domination number is bounded by a constant, not only 2, but any number that is bounded by a constant. So let's recall some terminology about hypergraphs. Here we use hypergraphs notation. By the way, are there any questions? No? Okay. A hypergraph H is a pair where V, the vertex set, is a finite set of vertices, and the hyperedges is a set of subsets of V called hyperedges. So if these subsets are of size 2, then we have the old ordinary graphs. For hypergraphs, any set of vertices might constitute an edge. So a vertex set X is called a transversal of the hypergraph if X intersects every hyperedge of H. So if these hyperedges are of size 2, then it corresponds to vertex cover, you can see. And it's called a minimal transversal if it is a transversal that does not properly contain any other transversal. So let H star denote the hypergraph with vertex set VH, having as hyperedges exactly the minimal transversals of H. So look at that hypergraph now, another hypergraph that we construct. So another definition, a hypergraph is said to be Sperner if no hyperedge of H contains another hyperedge. So the hypergraph transversal problem is the decision problem that takes as input two Sperner hypergraphs, H and H prime, and asks whether H prime is equal to H star. So it was proved previously that for every positive integer k, the hypergraph transversal problem is solvable in polynomial time if all hyperedges of one of the two hypergraphs, H and H prime, are of size at most k. So, and for every positive integer k, the following problem is solvable in polynomial time. Given a Sperner hypergraph, determine whether all minimal transversals are of size k. This was, it implies that. So how do we do that? So first we generate all the VH to the power k subsets of size k in VH. We then test for each of them whether it's a minimal transversal of H, and so therefore we obtain a hypergraph H prime. The problem now becomes that of testing whether H prime is equal to H star. Since all hyperedges of H star are of size k, the previous theorem implies that the problem is indeed polynomially solvable. So let's look at the recognition of well-dominated graphs. For every positive integer k, we prove that the problem of recognizing well-dominated graphs can be solved in polynomial time in the class of graphs with a domination number equal to k. So let G be a graph with domination number equal to k, and let's consider the hypergraph HG such that the hyperedge set contains the inclusion minimal elements of the closed neighborhoods of V. So take V and all of its neighbors, then the inclusion minimal elements of this. So the edge sets, like the hyperedges, are the closed neighborhoods. We can observe that HG is Sperner, and that the minimal transversals are exactly the minimal dominating sets of G. So then it's clear that G is well dominated because all minimal dominating sets have the same size, if and only if all minimal transversals are of the same size. So this can be, by the previous corollary, this can be tested in polynomial time. By the way, in another work, we also worked on while totally dominated graphs, which were also recently proven to be, the recognition of which was also recently proven to be co-MP complete. So by a similar proof, but this time having the hyperedges, the inclusion minimal elements of the open neighborhood of V, as opposed to closed neighborhood of V, we can have, by a very similar proof, we can also observe that recognizing while totally dominated graphs can be solved in polynomial time in the class of graphs with total domination number equal to the k. So if the total domination number is bounded by a constant, then we can also recognize while totally dominated graphs in polynomial time. So some open problems. So it seems to be a nice question to characterize graphs such that every irreducible dominating set is either a minimal dominating set or a minimal total dominating set. This comes from the concept of irreducible dominating sets. So similar question can be posed for well totally dominated graphs, the lexicographic products. So as I said before, well totally dominated graphs are graphs for which all minimal total dominating sets are of the same size. Characterizing the non-trivial lexicographic product graphs that are well totally dominated can be done in it can be a good open question, which is the equivalent open question for well-dominated graphs. This time, we would probably need the characterization of minimal total dominating sets in well-totally dominated graphs. And the concept of irreducible dominating sets could also play an important role here, because irreducible dominating sets generalize both minimal dominating sets and minimal total dominating sets. So if there are not any other questions, then I want to move on to this last work for the proofs, I'm not going to go into the details in the last two works, actually. I will move on to the next topic, almost well-dominated graphs, which is a generalization of well-dominated graphs. So almost well-dominated graphs, we define them as, we call the difference between the domination number and upper domination number as the domination gap of G. By the way, for well-covered variants of this was also studied, and they are called almost well-covered graphs. So in that case, the difference between the independence number and independent domination number, so the difference between IG and alpha G is called the independence gap, and all the other definitions are similar. So we call their difference as the domination gap and denote it like this. While a graph G with domination gap is equal to 0 means that the domination number and upper domination number are the same. It's a well-dominated graph. And a graph G with domination gap is equal to 1 is called an almost well-dominated graph. So it's a generalization of well-dominated graphs. So Finbow proved that a cycle with 4 vertices is the only well-dominated bipartite graph with minimum degree at least 2. Actually, he characterized all well-dominated bipartite graphs. And we can observe from their characterization that a cycle on 4 vertices is the only well-dominated bipartite graph with minimum degree at least 2, because all the other vertices have leaves attached to them in the other families. We proved that there exists so although there exists only one graph for well-dominated bipartite graphs with minimum degree at least 2, we prove that there exist precisely 31 almost well-dominated bipartite graphs with minimum degree at least 2. And we specify these 31 graphs explicitly. So while the results by Finbow have implications for almost well-dominated graphs with Gjörth at least 8. So in another work, we extend their results to C3, C4, C5, C7 free almost well-dominated graphs. So which means that if the Gjörth is at least 8, observe that C3, C4, C5, C6, and C7 are all forbidden. Now we allow C6 here for the Gjörth 6 graph. So it becomes C3, C4, C5, C7 free almost well-dominated graphs. So it's an extension of their results. And we give a complete structural characterization of such graphs as well. So of course, the natural questions that come here from these two topics is, of course, for the first one, a complete characterization of almost well-dominated bipartite graphs, because we characterized only almost well-dominated bipartite graphs with minimum degree at least 2. So all well-dominated bipartite graphs were characterized by Finbow. So we extended their characterization for almost well-dominated bipartite graphs for minimum degree at least 2 case. So if you don't have that restriction, and obtaining a characterization for the general case would be a nice open question. And okay, so we, with Gjörth, at least 8 here were characterized by Finbow, and we extended it a little. So if we remove also, if we allow also C7, so make this for Gjörth at least 6 case, this would be an improvement over our work as well, and it will also be, of course, an extension of Finbow's work, in which the ones with Gjörth at least 8 were characterized. So characterizing almost well-dominated graphs with Gjörth at least 6, and then going on from there and going to even 4 and triangle-free, almost well-dominated graphs, etc. It would be nice because bipartite, it would also be a more general than almost well-dominated bipartite graphs. I think it would be a little difficult for triangle-free, but I think for almost well-dominated graphs with GERD at least 6 would be a nice open question. So actually a lot of work, I mean, has been done right now. I mean, not too much, but some work, let's say, for well-dominated graphs. And we extended some of them for almost well-dominated graphs. But the existing works, the other existing works for well-dominated graphs can also be extended for almost well-dominated graphs. With GERD at least 6 or others, not only GERD at least 6, but others as well. So this is the end of my talk. So if you have any open questions, I can answer.
Thank you so much, Didem, for your nice presentation.
Thank
Many
you.
results I have seen in this presentation. Very nice.
Thank you.
Is there any question or remarks? Didem, you characterize a well-dominated graph with a small domination number, yeah?
Well-dominated graphs with?
You characterize, I think you consider well-dominated graphs with a small domination number. Gamma is 2 and 3 and so on, yes?
Gamma is, no.
I think you point on graphs with have gamma is 2, domination number 2, and
yes, well-dominated graphs with gamma is equal to 2 can be recognized in polynomial time.
Yeah, and
also a characterization, yes.
Okay, very nice. And what happened when we have a big domination number, you know?
In terms of characterization, okay, this is a structural characterization for well-dominated graphs with gamma is equal to 2. But we don't have a structural characterization for gamma is equal to 3, etc. But we just have that by using terminology on hypergraphs, we prove that they can be recognized in polynomial time. So for sure they can be. So it could also be a nice future work of having a structural characterization of well-dominated graphs with gamma g is equal to 3.
Yes, very nice. Okay. Thank you.
Because we know that they can be recognized in polynomial time.
Okay. And Didem, another question: why you consider lexicography? Why didn't consider another kind of product? For example, rooted product.
I don't remember the motivation at that time, but lexicographic product, I mean, for domination in product graphs, there are some works, but for well-dominated graphs, we didn't have any other works at that time. And for lexicographic products, it's easier to see because we have all the edges in between. We can, it's the easiest way to start with if we want to obtain a new result. But other product graphs would also be a nice question for well-dominated graphs because we have all the edges in between. We can say that, okay, if we select one vertex here, we can automatically say that all the neighbors are dominated, and because it was a nice and easier starting point. But Cartesian product, other product graphs can also be built upon this. So that would also be a nice future work.
Yes. Thank you so much. Is there any question?
Yes, Said, I have a question.
Okay, Hamid.
Okay, first of all, I would like to thank you for your nice presentation. And my question is, in your view, it would be possible to study total dominated graphs, independent dominated graphs, and so on. What do you think?
Well, totally dominated graphs, we also studied. I didn't put it in this presentation, but we have a paper on them about well totally dominated graphs. You can see them on my webpage. And in that paper, I mentioned about that in here, but in that paper, by a similar proof, we proved that well totally dominated graphs, where the total domination number is bounded by a constant, can also be recognized in polynomial time. We just adapted the proof, but this time instead of closed neighborhoods, we had open neighborhoods, and it worked. But we also have other structural results in that paper about well totally dominated graphs. But as a remark, I should say that if we have well totally dominated graphs, first of all, well-dominated graphs are a proper subgraph or subclass of well-covered graphs. And there are existing works in the literature, and we can bound because of the domination chain. You can make relations, etc. But if it's well totally dominated graphs, then we are totally it's a different class. So a well-dominated graph is not necessarily a subclass of so a well-dominated graph can be a well-totally dominated graph, but cannot be also. And similarly for well-totally dominated graphs, can be well-dominated, but cannot be also. So there's not a relation between the two. Yeah. So, and also in that work, we saw that obtaining results for well-totally dominated graphs is really difficult. I mean, we do have several results, but they are for specific cases. You can look at that paper. There are a lot of open questions. It's a more difficult problem, well-totally dominated graphs. And also for there are also a lot of works. I didn't put it in this presentation not to make it too long, but you can look at the paper on my website. It's called Well Totally Dominated Graphs. That's the name of the publication. So, yeah.
Okay.
That's also similar questions might be posed for well totally dominated graphs as well.
Okay. Thank you very much. And generally, you suggest to explore other versions or not?
For well totally dominated graphs?
No, I mean for example,
for another kind of dominating set.
Connected dominating or.
I didn't work on them. I also don't remember any other work. So I know that for irredundant sets, there is one work. They are called well irredundant graphs, which is even a special case of well-dominated graphs. But for other dominating sets, I didn't work on them for connected domination or other well cases of the other domination parameters. But I think they all could be nice questions.
Okay.
Okay. Thank you very
much. I'm not
much.
aware of any other work other than domination and total domination. This well case in the domination world, I'm not aware of any other domination variants about well something dominated.
Yeah.
Thank you very much for your perfect information.
Thank you.
Didem, Professor Didem. If there is no more question, please thank Professor Didem again. Thank you so much.
Thank you very much.